Greetings, everyone. Hopefully this is not too loud. Thank you for showing up today. So today I'll talk about opportunistic wireless communication, and particularly on how they pertain to natural disasters. So, to let you know briefly, actually, I forgot to set it up for right now, but typically with the stuff that I'm going to talk about today and the research platform that I'm going to go into, there's a mobile application that you can download for iOS. But currently, if you try that link, the link will work, but I don't think you can download the app right now. I'll have to set it back up for you. So here's some of the things I'll be going over with you all today. Just a background about why opportunistic wireless communication is needed. And then give you some information about the research platform, and then some future projects that I'm looking into. So many of us are fully aware of the natural disasters, especially those that have occurred recently. With Hurricane Maria and how it struck Puerto Rico, in 2016, Hurricane Matthew, and the destruction that it did in Haiti. In many of these places, there are a lot of deaths caused, in particular in Haiti. This is actually a picture from Haiti, where over 1,000 of the people there were killed when the natural disaster hit. And so within the last 2 years, there's been a number of natural disasters, and when these things occur, they typically knock out a wireless infrastructure. So the things that we typically depend on, like cellular communications, currently doesn't work in these type of environments. And so then there's also relief workers that's employed in these areas, and they have to establish some way to communicate with each other and with the people there to communicate food and water. So I want to ask one question. We have, I guess, hopefully it's over, the current snowstorm that hit. What would you all do if this snowstorm or the snowstorms that happened became extremely violent, or a natural disaster hit Lexington right now? How would you react? How would you communicate? Most people are going to go straight to their cell phones, right? So if you imagine that these dots here are people, they could actually be you, and we all have our mobile devices, and say we all have Bluetooth communication on those devices. So if we look at a few people in particular in this scenario, Alice, Bob, Carol, and David, we're going to see how they might communicate in one of these scenarios. So what's the first thing people do nowadays when a natural disaster hits? Say that snowstorm, that violent snowstorm I mentioned hits. What's the first thing you're going to do? You can blurt out an answer.
Tweet about
Twitter.
it.
Okay, tweet.
Find water.
Find water. Okay, you try to find water.
Check buy you feel good.
You said buy sugar?
Check in on Facebook.
Check in on Facebook, right? And so one of the first things people do when they have a natural disaster or some type of scenario is people check in on Facebook, right? But one of the things that's kind of hard with that is Facebook depends on the internet. When a natural disaster hits, communication on your cell phone is going to either be slow or it's going to be non-existent. So what if you can communicate using the people around you, right? And so saying that we're all sitting here, the natural disaster hits, after the disaster hits, we might move around certain areas. What if we can post messages to each other and people come in contact, and then they forward information using opportunistic communication? And depending on the scenario I'm talking about, natural disasters, it might not be as pertinent for this scenario, but if you need to do this in a secure fashion. So here, many of you might know this guy. If you've been around for a while, if you're looking more recently, you're like, why does the Verizon guy look like the Sprint guy? Because now he's currently the Sprint. But the notion that Verizon had when Verizon came out with these commercials is that bring your network with you. Your network's everywhere. And it's really opportunistic communication, trying to leverage this actual aspect. How can you leverage the people around you to actually communicate and really, in the scenario I'm talking about, create social networks? So what this is going around or supplementing centralized communication. So many of us know what centralized communication is. It's basically the cloud. But there's a lot of things that go wrong. There's the central point of failure, which I think, what was it, sometime last year, towards the end of last year, many of us faced when you try to go to some of these websites and there was a denial of service attack, right? So you couldn't go to your major websites like GitHub. But there's congestion that happens. You can have a lot of people in one area. Your phone says, your mobile device says you have LTE, but you can't communicate at all. You can't get on Facebook, you can't get on Instagram, et cetera. And then the kill switch, which I'll talk about in a second, the IP blacklister. And so one of the things I want to point out is that 60% of the world has mobile devices, and over 50% of the world are without internet. So there are a lot of people with mobile devices, and when we get in these opportunistic scenarios, how can we leverage those devices to actually establish communication? So the kill switch is actually something that happened in Arab Springs in 2011, I believe it was, 2011, 2012, where basically the people that lived in Arab Springs were trying to protest the government, and the government didn't like these things. People were getting on Twitter, and they were saying, meet in this location, we're going to come together and we're going to protest these things because we don't like them. And what the government did is they contacted all the internet service providers and they basically cut communication to the internet. So they called it a kill switch. And so it's kind of like a big brother approach. Basically, anytime you could think with this centralized communication, if you cut that one connection, people can't communicate the way they want to. Another scenario is actually FireChat, the FireChat application. So this, many of you might know about FireChat. FireChat got really big because at this Burning Man festival in Hong Kong, the government supposedly was trying to slow down communication in this area at the Burning Man, and people wanted to communicate. So they all downloaded this FireChat app, and they basically created a social network which was peer-to-peer to communicate with each other. So now let me go into some of the things that, some of the research that I do in the area, and some of the tools that I've developed to conduct research in the area. So the Alium Social Research Platform. So basically, this is the mobile application that was at the very beginning that I talked about. Alium, I'm a basketball guy. We're here at UK, it's perfect, right? So if you think about the notion of passing a basketball, or basically alley-ooping a basketball, that's what the application does, is passes messages. So it stands for, of course I added this on afterwards, but a low latency evaluation system for ad-hoc opportunistic passing. So Alium Social. So what this does is you can download on your application, on your iPhone. You don't need to jailbreak it. And it has a lot of functionality. So it allows, it's online, offline social networks, so it looks very similar to Twitter. So when you're online, everybody receives tweets like they normally would. When you're offline, people can route messages to each other using different routing protocols that's available in the application. And so routing protocols is basically, you can move messages based off of different social characteristics of the nodes inside the network. It operates securely. So basically there is encryption, decryption of messages using elliptic curve encryption, and they can do multiple DTN protocols that I mentioned before at the same time. So this is kind of, this application is just the platform itself, but it runs on top of a middleware that's developed. So this middleware allows you to do this routing over Bluetooth and peer-to-peer Wi-Fi. So here you see the Alium Social application at the top of the middleware, but basically any mobile application can run on top of this middleware. And the way it's set up is it has a bunch of APIs, and the orange is the different routing protocols that you can add. So one of the unique things about the routing protocols in here is that the middleware handles so much of the communication that you can write a routing protocol in less than 100 lines of code using Swift. And so everything else is handled, all the communication security that I mentioned is handled in the message manager and the ad-hoc manager. So there's other projects in the area that have done things in a similar fashion of creating middlewares. And many of those middlewares in the past, so the reason why this middleware is slightly different is because first, it doesn't allow jailbreak. You don't have to jailbreak your phone, and then actually creating different routing protocols to enable. Most of these things work with epidemic routing, which is basically flooding the message out to everybody that you get in contact with to disseminate information. So I'll give you a quick example of how this would work. If we go back to the scenario that I mentioned of what happens if a natural disaster occurred right now, right? And so if we actually would take it, say, a disaster right now in Marksbury, we have Alice. So Alice had created a message saying, hey, I'm safe. And she wanted to post it to her friends, I'm okay, but I'm just stuck in Marksbury because of the disaster just hit. Say she was snowed in. So say the people that are around her, the blue here is, say these are people that come by in Bluetooth range. And so R is for receive the message and F is a message forwarder. So then in a scenario, say it's an interest-based routing protocol, so basically you have to be interested in Alice's messages to forward. Eric is not interested in the message, so he doesn't receive it. David is a forward of Alice's message. Should have been two, I'm sorry. So David actually already had Alice's message, which is why he's at message 5. Bob was at message 2. So Bob received the updates from Alice in this particular routing protocol, and Carol is out of range. So you can say Carol might be at row, right? And so sometime in the future, say an hour later, say the people moved around, right? So some people were able to make it out of Marksbury. So in that scenario, David and Eric are still around in Marksbury, but say Bob got to Rupp where Carol was at. Carol was one of Alice's friends or family members. So in this scenario, when Bob comes in contact with Carol, he basically just forwards all the messages that he has for Alice to Carol. And so this can work with anything you would think something like this, like an emergency alert. Something like this could be broadcasted, but depending on the scenario that it's in, you can use different routing protocols to propagate information. How much time?
You have 17 minutes left.
Oh, so, okay, so I can. Okay, so here's kind of some of the underpinnings to enable something like this. Yes.
Yeah, sorry. It seems to me that the underlying assumption here is that the graph is connected over time.
Yes.
And is this realistic in this?
Well, so that's a good question. It depends. And so what this assumes is that you have the node, I'm talking about people in this scenario, that people are going to eventually move around and they come in contact with each other. So they don't have to be they don't have to be connected all the time or at one point in time, but they can eventually move and say one node. In the example I gave, Carol came in contact with David. And so David moved to another area. He walked and got out of Marksbury and walked over downtown to Rupp.
Yeah, I think it's called hurricane or Katrina or something who are stuck with places that we don't move that, in that case,
Well, so that's actually a good example. So in those scenarios, if you have, say all of us were creating tweets, for example, and one person made it out of here to Rupp. If that one person is carrying messages from multiple people, that one person can deliver a lot of information to Rupp. So in certain areas, of course, this is highly dependent on mobility, and you need some type of interaction, because if nobody makes that move, basically nobody in Rupp gets the information from Marksbury. But I'm actually going to talk about some future work of how different things can start to intertwine to actually increase message delivery in these scenarios. Yes.
I was just going to say, it seems like that making the emergency responders forwarders would be an excellent way to kind of get around that problem.
Exactly. So that's definitely a good one. So the emergency responders, since they're designated, since they're being deployed in these scenarios, and they are going to come with, say, some type of infrastructure, some type of movement, you can almost, I want to say, like, you can think that they can almost be the backbone of this type of network for this disaster scenario. So enable some of this, to enable some of these things, of course you need mobile devices, and one of my assumptions is that I assume a mobile device is a person, which people carry their cell phones everywhere, so it seems like an okay assumption. And then you need the cloud at some point, right? So when I said so online, offline social network, so of course when it's online, people will use the cloud mostly, but there's a limitation that is currently in the application when you need the cloud when you initially download the application. Currently for anything Android or iOS, you need to download the app the first time. And so I'll talk about that limitation in a little bit. But you need a cloud there to basically establish the credentials needed for security. And then you need some centralized authority, which is basically, in this functionality, there's some Node.js code to get some of these things working. And so the limitation that I talked about with depending on the cloud is what I call a one-time infrastructure requirement. So when you download the application and the user installs it, this is what would happen on two users' devices. And so what they do is they'll generate a public key, private key. Currently in the application, this is elliptic curve public key, private key. And the certificate, it'll generate a certificate signing request. This will go to the cloud. The cloud would then send that to the certificate authority, and the certificate authority would turn those into certificates and propagate those back down to the users. Here, now when the user has a certificate, they can operate offline without ever connecting to the internet again for the lifespan of the certificate. So this is a scenario of how two users would disseminate information. The example that I gave is, say Alice comes in contact with Bob. So they're basically advertising. Advertising here is basically broadcast mode. So remember I told you this works over Bluetooth and peer-to-peer Wi-Fi. So in Bluetooth, two users come in contact. Alice says, hi, I'm Alice. Her device says, hi, I'm Alice. Bob says, hi, I'm Bob. Bob says, I'm interested in the information from Alice. So he sends an invitation to establish a connection. Once Alice accepts that invitation, then Bob sends his certificate. Alice does the same thing. And from that, they extract each other's public key from that certificate, and now they can establish a secure connection from each other, and they can send the messages, any messages that's needed. And then Alice can encrypt it. So what Alice would do is encrypt all of the information she's sending with Bob's public key. So only Bob can be the person to see, and she would sign that information with her private key. And since Bob has her Alice's public key, you can then verify that that information came from her. So you can imagine how that would work going through multiple users. I'll give you a quick scenario on how that would work. A lot of this stuff is basically the same up to the connection being established, but here, this is when Bob is being selected as a forwarder. So say for instance, Alice is asking Bob to forward the information, and what he does is he keeps Alice's certificate. So say one question that comes to mind is, say that the person doesn't have Alice's certificate. In normal certificate authority PKI system, everybody has to agree or have the certificate information and say that I trust it. In this scenario, not necessarily. All you need to do is have, one thing I forgot to mention is that Alice's unique user ID is embedded inside the certificate as well. So as long as you know that user ID, once you receive the certificate, or you can verify if the certificate passes authority or passes approval, then you know when she pulled that unique user ID out of it, you know that that's really came from Alice. So here's when the messages are being forwarded between now Carol and Bob. So this is going through another user. When Alice information goes to Bob, and Bob is now going to forward that information to Carol, now this goes through, when they establish a connection, Bob will give Carol Alice's certificate, even though she might not have seen this exact certificate before from Alice. And what she can do is verify the messages and know that they actually came from Alice without being in contact or without establishing another connection to the cloud, yes.
So can't Bob just copy Alice's certificate and use it as if he were Alice?
No, well, he can try to use it as Alice. He doesn't have the private key. So what happens is Alice's unique ID is embedded in that certificate, and then that public key is the only information that he has access to. So he can attempt to sign something with the public key, but then you would need the private key to verify it, and vice versa. And so, in order to verify the information, the only information that's there is Alice's public key, and you can use that public key to verify to decrypt private information, and also to verify that information came from Alice. But you can't do anything else with it. So everybody else can save it, but unless you, in this sense, if you have the certificate authority initially, that would be the only way you would get through you would be able to forge information from Alice. So here is actually some results from some of this. So actually, this is some of the work from, or these results were gathered from Gainesville, where I was in grad school. And so here, there was 10 people that used the application. It was about 80-something people who downloaded the application. But of course, with this application, as Bodie mentioned, there usually needs some type of density, right? And so I had 10 users using this application consistently. And so this is the city of Gainesville, and to give you some perspective, the point all the way up there is Gainesville Airport, and in the middle is the University of Florida campus. So the blue dots here are where messages were created. So users were going around 7 days, and they were basically creating their own tweets. They generated information like how they would in social network. So they said, hey, I'm getting pizza right now, or I'm doing something similar like that. Red is when at least 2 nodes came in contact and information was disseminated. And so you see, like, a lot of the dissemination points happen in similar areas. Like, actually, the ones in the middle is kind of similar to the student, right around the student union at University of Florida. So here is kind of the graph that the users created on their own. So basically, when users download the application, of course, many of the people I knew beforehand, some of the ones that use it the most were my friends. But basically, I said, you follow who you want to follow. You don't have to follow who you want to follow. So here, when people set it up, or when people selected who they wanted to follow, they basically created a network density of about 64% within the network. And there was 2 center nodes, which is 6 and 7. And so 6 is me, and I think 7 was probably my roommate in the network. But basically, almost everybody knew us, so they all followed us. So here this kind of gives you some insight on. This is, if you think about the interest-based routing protocol, which is what I'm going to show you the results on, this gives you how people follow each other, so who they would be interested in, but it doesn't tell you exactly how messages would be disseminated, because people have to actually come in contact and disseminate that information. So here we're looking at some of the delay in delivery results is in this network, I forgot to mention, that I think I showed it on the next slide. But about 200 and something messages, oh, there it is. So 259 messages were created, and individual messages were created. 796 messages were propagated through one hop. So remember that multiple users are interested in more than one information. So out of those 259 messages, they might have multiple delivery points because it's like a publish-subscribe Twitter type system. So 167 of the messages were propagated and were more than 2 hops or more, so that you know that there was routing in these scenarios I'm going to mention. So in that, 25% of the messages were delivered within less than an hour, which for 10 nodes in here for over 7 days is actually pretty good, especially when you see that people actually go to sleep even though they were grad students at the time. They did get some sleep, so those delays in there are things that you typically don't find in simulation environments, because usually these things will be simulated. 43% of the messages were delivered within 24 hours, and then 90% of messages were 94 hours, so it took some time for the rest of those messages. And then when it looks at delivery, 30% of the messages that were meant to be delivered, or 30% of the messages had an 80% delivery rate. So based off the following relationships, or who selected who to follow, the messages that went out, 80% of those had over 30% delivery rate, and 50% of 70% of messages were delivered. So all messages are not intended to be delivered to everybody, so some of them had a higher delivery rate than other ones.
So are these results good, you think?
I do think they're good for the scenario that was there for 10. It was 10 people moving over 7 days. One of the things that I'm doing, or that I'm looking at now, is having more routing protocols, more nodes over a longer duration of time. But they're typically good when you look at how people do simulation environments, because you have nowadays people are still, they either have some realistic mobility pattern or they're using actual data that was collected from mobility, but then you just hit run on the simulation and you don't have real-time delays. So when you look at that, what did I say, on 25% of messages delivered within an hour, that's pretty good when you look at 10 nodes, and the area of that map was huge. So I do think it was pretty good for this scenario. So this is kind of how I fared, how you would compare against how routing protocols have been evaluating simulation. Here is 10 nodes. I said the range was probably around 5 to 50 meters. They use Wi-Fi and peer-to-peer Wi-Fi and Bluetooth. And in simulation environments, these are some of the protocols that are well known in this area, and these are kind of how they set up their simulation environment. So if you see here, the 88 kilometers, that was a large area space compared to what's typically simulated with a larger communication range and a larger density of nodes. And that's it. So some of the future work that I'm looking at, and so of course this is a middleware. So the good thing about the middleware is that you can essentially run any application on top of it. So if you think about, I created a social networking application, but if you think about Facebook, Instagram, Twitter, who already has a large population of users, they adopted this. All they have to do is run on top of the SLS middleware, and then you automatically acquire that density of those types of networks. The other thing is for medical applications. So I talked about natural disasters in places that have limited communication. How can you collect and forward medical information to doctors? So normally people can't say can't see their doctor. They can only see a doctor once a month in these developing areas. Now you might be able to decrease some of that time if you correctly secure and use other people to disseminate information, medical information. One of the other things too that kind of goes to the point of how do you increase communication in these scenarios is one thing that I like to call low-cost smart city. So you can actually deploy certain things around the area in these developing areas to actually increase communication or use the people there as communication. So say, for instance, these circles and squares here with numbers in them, you can think about those as particular buildings. So those are stationary buildings. And you have a natural disaster, what happens is people form certain types of mobility. So here, the red here you can think is messages are not getting through that well. So they're under a certain threshold. They have a probability of, say, 0.62. Green is where people are creating paths, but and those are really good paths. So you would think if there's a food source in a natural disaster between here and say the next building, people are going to traverse that path a lot, right? But then they create fragments in the network because people won't go to other areas where it might consist of people being stuck, but they don't have food or water. And so if you can do stuff where you start deploying drones, which is this blue line here, you basically you understand the network topology, and you can start deploying drones to facilitate communication in broken routes. So if you looked at that previous one, that route that drone set in was a 0.33 route, and basically didn't have a lot of people going before through the network. But you can use drones or other communication to say, if you cover this path, you can increase throughput within the whole network. And with that, that's the end of the talk. If you guys have any questions, I'm going to take it. Yes.
So in your experience,